This video will begin the video series on Chapter 17, dealing with carboxylic acids. So let's first take a look at the structure of carboxylic acids, and the easiest way to do so is to compare them to a structure that we've already looked at. So we're going to compare carboxylic acids to aldehydes. Now, we already know that aldehydes are, the carbon is trigonal planar, so it's sp2 hybridized. We know, we've already seen the bond angles of the hydrogen carbon oxygen bond at 120 degrees on both sides, and of course the hydrogen carbon hydrogen bond is 118 degrees. So the way that this plays out when we take a look at carboxylic acids, we might, try to think about any possible bond changes, and there are really very small bond changes. We see that the oxygen carbon oxygen bond angle is 125, so it's a little bit wider than that of an aldehyde. Simply because there's a little bit more repulsion between the two oxygens. And then on the other side, the bond angle between the hydrogen carbon hydrogen bond is 124. So again, still just a little bit wider, but not by much, which means that that hydrogen carbon oxygen bond at the bottom is a little bit smaller at 111 degrees. So the hybridization of the carbon is the same as that of the aldehyde. It's sp2 hybridized, which means that that carbon is also trigonal planar. So we're dealing with planar structures here. Now, one interesting aspect of carboxylic acids is they have two different conformations. Now, what do I mean by this? Well, if you take a look at the OH group, that hydrogen can be oriented in one of two ways. It could be oriented up, kind of closer to the carbonyl, or it could be oriented down, away from the carbonyl. Now, we call these conformations S-cis and S-trans. Very similar to when we were looking at conjugated dienes. And it happens that there's actually an energy barrier to go from the S-cis to the S-trans, and that energy barrier is 13 kilocalories per mole. And so you see that my equilibrium arrows, I'm showing you that the S-cis is actually more favored. And that favorability is by about 6 kilocalories per mole. Now, there are a couple of reasons for this. One of them is assumed that there's some type of interaction between the carbonyl oxygen and the hydrogen. This has never been really played out. Probably the strongest reason for this has to do with the interaction of two carboxylic acids. So if I draw a carboxylic acid, here I'm using, this is called formic acid. Very similar to formaldehyde when you have two hydrogens coming off of the carbonyl carbon. If you have a hydrogen and an OH, it's formic acid. And if I draw another formic acid molecule, but I simply flip it around and I orient the OH next to the carbonyl, and then of course the carbonyl on the structure on the right next to the OH on the structure on the left, you can see and kind of visualize that I can get hydrogen bonding that's occurring. And this certainly happens. We can actually determine this spectroscopically. This is called dimerization. So when two carboxylic acids, especially simple carboxylic acids, are interacting with one another, they can dimerize, and this this really stabilizes the S-cis conformation of that carboxylic acid. So it also gives carboxylic acids much higher boiling points than we would normally think. Now, just to show a comparison, If I look at the boiling point of ethanol versus the boiling point of acetic acid, obviously acetic acid has a little bit higher molecular weight, but they're relatively similar in structures. I've just added a carbonyl group. And we've already discussed alcohols and the boiling points of alcohols. Ethanol has a boiling point of 78 degrees. So if I compare that to acetic acid, I see the boiling point of acetic acid is 117 degrees. So we're talking about 30-degree difference and higher boiling point. And the reason comes from having to add energy to break the dimers apart before you even think about any other intermolecular interactions. So through the rest of the chapter, we're going to look at how we make carboxylic acids, and then how we can react carboxylic acids to make other things.